Let's discuss the chi-square goodness of fit test. The chi-square goodness of fit test is used to compare a distribution of outcomes to an expected distribution of outcomes. So let's do this kind of simple example as a first step. In an attempt to determine if a die is fair, it's rolled 60 times and the results are analyzed. If the die were fair, you would expect to see, of course, exactly 10 of each of the frequencies. However, there will definitely be variation from that, and I have recorded the results in this table. So you'll see here that 1 showed up 5 times, 2, 13, and so on. Now again, we would expect all of these numbers to be 10, but for sure we know there'll be variability, so we aren't surprised maybe by some of these. 8 is real close to 10. 13 is real close to 10, but is 15 too far away? Now, in some respects, the chi-square goodness of fit test always reminds me of like a one proportion z-test, but with lots of different outcomes. A proportion test is always you're checking one proportion. You're saying, I thought P would be this, but I think that one proportion might be bigger, smaller, or not equal to. Well, I thought that a 1 would show up 10 times. But I also thought a 2 would show up 10 times. And I also so I have all of these things that I thought would happen, and I want to overall compare them all at once. Are they too different from what was expected? So this is where we use the chi-square statistic. And the chi-square statistic is a very nice simple formula. This, first of all, is the symbol. So you see this Greek letter chi squared. And simply we take what actually happened, we say the O, or observed, minus what we expected to happen. So essentially, how different are each of these values from what was expected? And then we square it. And the squaring is simply to eliminate the negatives. And then we do this as a proportion of what was expected. Now, before I calculate this, I wanted to answer these questions. First off, what values can our statistic, meaning our chi-square, take? Well, looking at the formula, I just want you to notice that this, because of being squared, will always be positive. At a minimum, if every single one of these frequencies were 10, we'd have 10 minus 10 squared. 10 minus 10 squared, and we would just have 0. So our chi-square statistic will always be greater than or equal to 0. We're never going to have negative chi-squares. This number, chi-square, will get very large when these numbers are very different, right? If we have a big difference here and square it, our chi-square numbers will get big. So if our observed is far away from what we expected, and likewise, what will cause our statistic to be very small are very tiny little differences between these two. So if our observed is close to what we expected to see. Now, I'm going to really quickly calculate this chi-square statistic. So here you can see I wrote down my calculation using the formula. It, of course, is the sum of all of these. So the observed minus the expected squared divided by for the first face and second, third, fourth, and fifth, and sixth. This calculation comes out to be 8.8. Now, similar to the t statistic, the chi-square statistic also has a degree of freedom. I'm going to write down that my chi-square was 8.8. The degrees of freedom here are a little bit different, because before we would say, well, how many things were in the sample size, and we would subtract 1, and you'd say, well, I did roll the dice 60 times. Instead of the number of rolls, it's instead 1 less than the number of categories. I had 6 categories, 6 faces. It's 1 less than that. So it's 5 degrees of freedom. So you're always going to count your number of categories and then subtract 1. Now, this is obviously able to be done on our calculator, but I did want to show you this off what's called a chi-square table. So let me let me show you really quickly. Remember, 5 degrees of freedom and 8 points. So here's our chi-square statistic. Please note the shape is very different than the normal curve and t-statistic. It's very skewed. And the reason is small chi-squares should lead to large p-values. A lot of evidence that we're not going to reject, which I know I'm getting a little ahead of myself. We'll fill some of these things in a minute. Well, we were at 5 degrees of freedom. So our 8.8 falls right in here. Let me put a little highlighter. Falls right in between these two p-values. So that would mean, if I just scroll up here, that my p-value is somewhere between 0.15 and 0.10, or rather 0.10 and 0.15. And a p-value that large is almost certainly going to lead to a failure to reject. Let's standardize this and formalize this. Here's how we run the goodness of fit test using the same kind of steps we've used for all of our other tests. The state, our null hypothesis, the observed distribution of dice roll outcomes is what was expected. The observed distribution of dice roll outcomes is different than expected. All right, I have filled in the null alternative and the plan step here. The null, the observed distribution of roll outcomes is what we expected, and the alternative is the observed roll outcomes is different than expected. Please note, this is like a fill-in-the-blank kind of null and alternative. I would always start by saying the observed distribution of whatever you're studying is equal to what was expected. The observed distribution was different or not equal to. We'll never say less than or greater than here, because think about the dice rolls. The minute I told you that we only got 5 ones, you automatically knew one of the other faces was bigger than 10. So you can never say greater than or less than, because some will be smaller and some will be bigger. In terms of our conditions, we still have the same old sample size less than or equal 1/10 all rolls. The second condition, the one to ensure that we sampled enough, is that our expected counts, all of ours were 10, had to be bigger than 5. Please note, there's nothing here about independence, because of course, the minute I told you, hey, we had too few ones, you'd say, well, then I know something about the other faces. So nothing independent here. We set our chi-square statistic with 5 degrees of freedom was 8.8, and therefore our p-value was somewhere between 0.1 and 0.15. And no matter what significance level we've ever talked about, that would lead us to fail to reject, because the p-value is larger than, I'll use 0.05. So we don't have enough evidence that the dice isn't fair. Now, if we have a TI-84, we can certainly do this calculation with that calculator. Let me show you how. So the first thing to do is to put your information in list 1 and list 2 when you want to do this on your calculator. In list 1, you should put your observed values, and in list 2, you should put your expected. So I just put in the observed frequency of the dice faces, and I put 10 for all of the expected dice faces. Then we'll go to the stat menu, over to tests, And we will scroll all the way down until we see chi-square goodness of fit. And you'll see here there are two chi-squared, but we're doing the goodness of fit, so GOF. Hit enter. I put my observed in list 1. I put my expected in list 2. Now degrees of freedom, unfortunately, we have to figure this out. So it's 5, one less than the number of categories. So we had 6 faces. And I don't need to draw it, I just want to calculate it. And there is our chi-square. It's 8.8. And what's nice is my calculator gives the contribution, meaning how big was each difference in my calculations. So you can see that the one face and the 4 face each contributed quite a bit towards my statistic. But my chi-square was 8.8 and my p-value was 0.117. I'll have other examples of the chi-square goodness of fit test. If this helped you, please like and subscribe for more math help.